Morning. I'm Pranava Swarup and from 6th Sem B section CSE department, and this is my video assignment for the subject System Software and Compilers. Today we'll be solving a problem that is generating an object code for the following SIC source program and writing the object program. As you can see here, we have the program itself, and there's a label field, opcode, and operand field which is given, and I've included two other columns, that is location counter and object code. There are four types of instructions, and based on that they take the specified number of bytes. That is, type 1 takes 1 byte of storage, type 2 takes 2 bytes, type 3 3 bytes, and type 4 4 bytes. So based on the bytes they take, we'll write the location counter, that is sum start 3000 as the first instruction, so 3000 is the starting address, and hence in location counter we include 3000 first. And then clear instruction is type 2, which takes 2 bytes, so we add 2 bytes to 3000, that is 3002. And LDA is type 3, so we get 3005, we add 3 to 3002, and hence we get 3005. And plus LDB is type 4, so we add 4 to 3005, hence we get 3009. And after that all these instructions are type 3, so it keeps incrementing by 3 as you go to the next step, which is how we've got the location counter table filled. Here we have different opcodes for different instructions. So opcode for clear is B4, for LDA it's 00, for LDB it's 68, for JLT it's 38, for RSUB it's 4C, for add it's 18, for TIX it's 2C, and for STA it's OC. We'll be using this opcode to write the object program in the next step. Here we have the first instruction, that is clear X. The label is first, opcode is clear, and operand is X. Clear is a type 2 instruction, so we have opcode R1 and R2. R1 and R2 are two registers of 4 bits each. So the opcode for clear instruction is B4, which is 10110100 in binary, and the object code for this instruction is B410, as you can see. So the next instruction is LDA #0. This is immediate addressing mode and there's no displacement, so we fill the 12-bit displacement field as 0. And N is for indirect addressing mode, I is immediate, X is indexed mode, B is base relative addressing mode, P is program counter mode, and E is 0 for type 3 and 1 for type 4 instruction. Since this is type 3, E is 0, and I is 1 because it's immediate addressing mode. So the opcode for LDA is 00, which gives this object code for the instruction 010000. Okay, so the next instruction is plus LDB #total. The opcode is plus LDB and operand is #total. Since it is plus, it's type 4 and hence E is set to 1. And I is 1 because it's immediate addressing mode. And we have 20-bit address since it's type 4. So the address is 478B. That is the address of total. As you can see here, total is at the location 478B. So we use that as the address. And hence the object code generated is 6910478B. The next instruction is add table comma X. The opcode is add and operand is table index. So this is type 3, hence we use a 12-bit displacement and not the 20-bit address. Since this is indexed addressing mode, X is equal to 1, and we put N and I is also 1. E is 0 since it's type 3, and we check for program counter relative mode, hence P is 1. We first find the displacement, that is the table value is at 0301B, and the PC value is the next instruction, that is 300C. So we subtract that and we get F, which is in fact between -2048 and 2047. So P is 1 and the object code we get is 1BA00F. The next instruction is TIX count. The opcode is TIX and operand is count. So TIX opcode is 2C, and the first six significant bits we take, so it's 001011, and this is type 3, and hence we use 12 bits. So it's not immediate addressing mode as well as indirect, so we put N and I as 1, and since it's not indexed addressing mode, X is 0, and since it's not base relative addressing mode, B is equal to 0, and we check for P, that is if it's P's program counter relative, and the displacement is 3018 minus 300F. 3018 is count and 300F is the address of next instruction, and displacement is 9, which is in the range to minus 2048 to 2047. So we put the P bit as 1, and the 12-bit address contains 009. I mean 12-bit displacement that will contain 009, hence the object code is 2F2009. The next instruction is JLT loop. Here we have the opcode of JLT, that is 38, so we take the first 6 bits, and N and I is set to 1 since it's not immediate and not indirect, and X is equal to 0 because it's not indexed addressing mode, and B is 0 because it's not base relative. We first find the displacement, that is 3009 minus 3012. Here 3009 is where loop is stored, and 3012 is the address of next instruction, that is program counter value, and we get minus 9, which is in the range minus 2048 to 2047. So the 12-bit displacement is FF7, hence the object code for this instruction is 3B2FF7. The next instruction is STA total. The opcode is STA and total is the operand. Opcode for STA is 0C, so we take the first 6 significant bits, that is 000011. And then I is set to 1 since it's not immediate and indirect mode. X is set to 0 since it's not indexed addressing mode. And this is base relative addressing mode, so B is set to 1 and P is set to 0. E is 0 since it's type 3, so we use 12-bit displacement. And we find displacement by using the base, which is base minus address. As you can see, total is the base, so we find the total address, that is 478B, minus address, which is again 478B, so we get 0 as the displacement. So we store 0 in the 12-bit displacement, and hence the object code we get for this instruction is 0F4000. Next we have R sub, which is 4C, the opcode is 4C, and the object code for this instruction is 4F0000. And the next instruction is RESW, which is reserve word. We don't calculate object code for that. We have two more reserve words and we don't calculate object code for that as well. And the last statement is end, which is an assembly directive, so we don't calculate object code for that too, but we write object code as 0000. Since we finished filling the object code part of the table, we can proceed to write the object program, which consists of three parts, that is header record, text record, and end record. Column 1 of header record contains head, that is to specify its header record. Column 2 to 7 is program name, here it's sum. Column 8 to 13 is starting address, that is 3000. Column 14 to 19 is length of object program in bytes. Here length is 178E, that is 478E minus 3000, which is ending address minus starting address. Then in text record, column 1 is T, column 2 to 7 is starting address in this record, that is again 3000. Column 8 to 9 is length of object code in the records in byte, which is 18. So we have 69 columns to use in the text record, but we've consumed only 48. So for one column is 2 bytes, 48 columns is 24 bytes, hence 24 in hexadecimal is 18. So that that 18 is what we fill in column 8 to 9 of text record, and column 10 to 69 is the object code. As you can see, this is the object code with separation for each instruction. And end record column 1 is is to specify it is end record, and column 2 to 7 is address of first executable instruction, that is again 3000. And with this we end today's video. Thank you. Please like, share and subscribe.